Good afternoon. Michael Stadler, CTO and co-founder of Xendee. We are a software engineering company out of San Diego and really support our clients from the beginning of a renewable energy project, micro project, down the road to conceptual design, techno-economic design, and also control. And today I want to talk about a model predictive controller for a PV battery microgrid system. And it's one of the challenging projects that we implemented because it's a very volatile system, because it has only renewables in it. And I want to demonstrate at the real implementation here in San Diego, at the University of California, San Diego, on how the system works and the benefits that we can achieve. Most microgrids at the moment, of course, are designed with certain assumptions in mind. Like you want to do a cost reduction, you want to do demand charge management, time of use cost reduction, or you want to increase the resiliency, right? Or you want to charge at certain times. And you have certain assumptions in mind when you do this. Then when it comes to controlling those technologies or microgrids, currently, most of the time, the controllers that you can purchase or implement are completely disconnected from the design phase. And this creates some challenges because the ideas that you had during the design phase are not necessarily reflected in the controller, and you get actually not the benefits that you were expecting. And the other thing is that every controller out there that you can purchase at the moment is not really doing forecasting, or not the reliable forecasting. This means it's just balancing the system at the current time step. It's not forward-looking, which means you're actually losing some opportunities here, because with such controllers, it's really not possible to do cost management. And we overcome this with an integrated planning and control platform, which guides you from the first step to the control within one platform, easy to transfer from one step to another, and also data transfer, which makes it easy. And this also guarantees to some extent that we get the results that we're planning for, because we use the same methodology and the same math and assumptions in the planning phase like we're using in the controller phase. And the other thing which is very important is that the controller needs to be adaptive and needs to factor in near-term changes in the weather conditions or in the load, so that we can do active demand charge or cost management reduction, or even CO2 reduction if we have fossil-based technologies in the mix. Before I jump into the details of our controller and the project, here a little bit about the different steps that you will encounter when you do a microgrid or DR project. The first step is probably you have an idea and you want to propose a project. And for this, you want to do some screening, right? And you can do this with a proposal tool that we have called Propose, which is very form-based and database-driven. It really helps you to offer services, your technology, or your project to a certain client. But then there's also this screening or analysis of multiple sites or technologies. So we have an application programming interface, an API, which allows you to interface directly with our backend, so that you can send a lot of data directly to our optimization engine without the need of entering this manually. So let's say you're a vendor and you want to figure out if your technology fits a certain market, or if it will benefit from certain incentives. You can do a lot of sensitivity runs around this by integrating Xendee optimization into your process, and you can send your data directly to our site. Or another use case would be you have multiple sites or hundreds of sites, and you want to screen a certain region, and you want to figure out where to place your technologies to achieve your highest return on investment. You can easily do this with Discover API. But then when you have figured out where you want to do something, or if you already sold a project or convinced someone, you can use our design product, which uses the same math and assumptions like the other tools before, to really do a very detailed techno-economic design. You can figure out the size of the battery, other technologies, up to 25 technologies, not only on the electricity, but also on the heating side and the cooling side, hydrogen, and how much they can contribute for cost reduction or CO2 reduction. You can even design your transformers or cables here. And when you're done with this, you can, with the click of a button, move your project into operate, setting up your controller, which is a software-based controller, and I will talk about this later on a little bit more, and start collecting data and control the technologies with the same assumptions in mind that you had early on to achieve the highest return on investment. So, but today I really want to talk about this model predictive controller, as we call it, the MPC, which creates an adaptive behavior. And at its core is an optimization engine, the same optimization engine that we have on the other products, just using real-time information. And it runs every 1 minute. It basically collects load forecasts and PV forecasts that we are providing through our AI-enabled engines, combines it with tariff information, other information, regulatory constraints, and basically optimizes the system just from a dispatch perspective for the next 3 days on a 1 minute time basis. And sends that information to the underlying physical system through a communication system, so that the underlying technologists can implement the strategy here for cost or CO2 savings. And key here is really this integration here. We worked with a couple of companies to be part of their hardware controllers, existing hardware controllers, so that we can easily integrate and send that information, read information, but we can also integrate our own Linux-based gateway for this. So this physical system provides us with new measurements after a minute. We built a new load forecast, PV forecast, combine it again and optimize again. And now for a moved horizon, because we moved 1 minute into the future basically, and in this way we can create an adaptive behavior, because every minute we get new information, we adapt ourselves for changes on the electricity load, weather conditions, and in this way we can already now do something about something that we expect down the road. And a rule-based controller or a controller without these forward-looking capabilities cannot do this. And in this way we achieve the higher savings, and this is what I'm going to talk about today. The Xendee platform, as I already said, is very integrated. It moves you from one stage to another. We use one code basis, which has the advantage that if we program a new feature on the planning side, it's automatically showing up on the operate side. And the other very important thing is that lessons learned on the operate side will immediately be fed back to the planning side and improve the quality of the planning tool. So our operate product, the MPC, follows the IEEE 2030.7 standard, which we co-wrote a couple of years ago with some national labs and universities. And it's a layered approach. And we are layer block free, which is in our case software-based. We can also be installed locally, but for maintenance and so on, it's actually better to do this through the cloud as we do it. Block one is really existing hardware controller. So when there's a good chance when you purchase an inverter for your PV system, it already can do voltage, frequency control, or even island. So we rely on those functionalities. Our MPC does not do all these things. We sit on top here. And block two is basically a communication layer, so, as I said, so that we can communicate, and then we crunch the numbers and send it back down. Block four is an interface to utility if needed for information exchange. Before I jump into the real project, I want to give you an idea on how challenging actually it can be to successfully implement a microcontroller project here. The first thing is you need to collect historic information if it's an existing site, because you want to estimate actually the benefits of a control strategy, right? And you need to know what the controller should do. So data collection about existing technologies, load profiles, or historic outputs is important. If you have a greenfield site, then you can actually get the data from Xendee's design tool, where you simulate all this, moved automatically here into this data acquisition part so that you can make a start. When you're done with this, you need to build your AI engines or forecasting engines for the load profiles, electricity loads, heating loads, if you have a more sophisticated microgrid, and of course for renewable energy output. We had to build this with our first projects a couple of years ago. Now this exists, but when you have these AI models, you want to start training them. And for this, you need the data. When you're completed with that, you need to integrate the system reliably in on-site either through an existing hardware controller, and we work with a couple of companies to do this. But at the end of the day, we need to be able to send data and receive data. And when all this is done, we can start testing the system, a so-called open loop test, where we crunch the numbers and see how the system works, but we're not implementing it. That's actually a simulation environment, which allows us to also test the benefits of such a control system. And that's very key, and I will get back to this later on. Not every site will benefit the same way like UC San Diego from a model predictive control system. It will depend on the spread between the time of use rates, how big a demand charge is, and also the volatility of the renewables and the forecasting errors. So before you implement such a system, you really want to do a simulation to mitigate problems later on. When this is all settled, you close the loop, you start controlling the system, and you record the benefits. And we always do this by comparing this to an existing control system. And you will see this later on with the UC San Diego implementation. They have already a Greensmith system, which is rule-based. We can simulate that benefit in parallel to what we are doing, and in this way, we can easily assess the real savings here. But overall, the point here is this can be a lengthy process, and the first time as we did this, it took more than a year. This was a couple of years ago with our first implementation. Now we're down to a couple of weeks or less than a week, depending if you already integrated in terms of communication with the vendor. And the future is actually to be faster than a day with this full automation and standardization so that we can handle a large number of projects here. So this is not a real site here. It's the university. It's a site at the University of California, San Diego. It was actually a project by CalTestBed. It's a California funding source which allows technologies to be tested. We already had a couple of implementations and real projects, but with this project, we really got the money and the time actually to test the implementation, the sophistication and savings in a very structured way here. And it's a warehouse with photovoltaics and battery system. They already have this existing Greensmith system, which is an energy management system, but it's not forward-looking. We just ride on that GEM system, provide the forecasting and our operate. So basically, between July 23 and May 24, we could test the whole system. We could test the data acquisition, the reliability of the communication, and also test the forecasting engines and compare it against the existing situation. This is actually a challenging case, and again, I will talk a little bit more about this later on, but it has only PV and battery, and this means it's highly volatile because of uncertainty of the PV output, and this makes it a very interesting control challenge, actually. So the economic goal was really to maximize the energy costs savings by utilizing operate, and as I said, James, the existing box has no foresight. So basically, it charges the battery when there's enough energy, and when the battery is full, it will either sell it to the utility or it will use it on site. So there's no foresight, no coordination of cost reduction, and that's actually a lost opportunity. We're missing an opportunity here. On the other hand, with the operate model predictive controller, we can forecast the load and the PV output, and with this foresight, we can try to actually actively manage the costs and the demand charges. But of course, with forecasting comes a forecasting error, and this again needs to be mitigated, right? And at the end of the day, the spread between the high price and the low prices and the demand charges in combination with the forecasting error will determine how much you can save at this site. And this is why it's so important to actually do simulation for each site before you go into deployment. But for our case, we have for every month a nice spread. We also have an active compensation for forecasting errors in combination with this loop, which will create a nice result. And here's the first result. At the bottom, we have the Greensmith, and at the top, we have our forecast as our MPC. And as you can see, it completely flattens the demand charge to 24 kilowatts on these days compared to 74 for the Greensmith. So this is already an indication how you can save money. And by the way, this is I would say, a small-sized project. I mean, we can handle everything from kilowatts. We deployed the system. We actually deployed the system for a residential site, which is even more challenging than this. But we can go also to very large systems. So the size doesn't really play a role in this. It's more like about the quality of the forecasting and the algorithms to control these technologies. So the overall savings for May, it was the last month of our test here. On the left-hand side in blue, we have here the rule-based controller, the Greensmith, and in green we have the MPC, the upright MPC from Xendee. And as you can see, we are saving here at the non-coincident dimension, basically on the highest peak in every time, by 8 kilowatts. Doesn't look much, but with 16 kilowatts is some saving, and you can also see that we're doing actually worse here at another period, but if we're not doing worse, what the controller does is it tries to shift from high-priced periods to this low price or less pricier periods, and in this way we can save money. We saved 9% in demand charges, and it was a little bit challenging here also because this is a way oversized system. The PV system is way too big compared to the load. And we didn't use design for the Xendee design for the designing the system, so it's an older system. And that's also a challenge because if you have such an oversized PV system, you have less room of demand charge management because naturally this large system already contributes to some extent to demand charge cost reduction, time of use rates, depending on how they are set up, right? But when it comes to sales, it was very effective. So the controller actually managed to sell 83% more energy than with the Greensmith system alone, and this actually came down to almost 80% cost savings for the month of May. But as already alluded to, different months different savings depending on the volatility forecasting errors. But we also have seen savings for other clients, for example, the Midwest, with 60% demand charge cost saving. So again, this is an indicator that before controller deployment, some simulation and optimization might be needed. And key for the success of such a control system is really the forecasting engine. And we have multiple AI-enabled forecasting engines, and they will be trained with the historic information. And then the best performing model will be picked because different use cases, different sites will have different outcomes with the different models. And here you see this. This is again for UC San Diego. This is a 48-hour forecast into the future. So here at midnight, we do a 48-hour forecast in the future. In this case, we're not updating it just so to show you how this works, because otherwise it would be a little bit too complicated. But here in black, you see basically the observed electricity load, and then in these dotted lines are these different models, AI models. And the red one is the premier model, which got selected with the best performance metrics. And as you can see here, this peak gets nicely captured because it will determine the demand charge. Off peak, a lot of volatility in around the forecast, or the forecast is more like an average approach, but it doesn't really matter because the costs are not that high. So it's really a fine-tuned model which helps you to capture the important times here for forecasting. The other important thing is really this active utility mismatch compensation. And I already alluded to this a little bit, that this can be a challenging case because we have uncertainty on the PV, we have uncertainty on the load, but the only controllable source that we have is the battery. And if there's a mismatch in the forecasting, basically it needs to be balanced by the utility. And the reason why I'm saying it's challenging because we have a patent pending adaptive demand charge correction, but the more you cycle the battery, the more you actually reduce the lifetime. So there's also a trade-off between lifetime of the battery and actually this forecasting. And all this needs to be factored in a simulation before you actually deploy a controller. And so with this adaptive demand charge correction and this loop for every minute, we get a kind of rolling dispatch, which gets updated every minute, which mitigates the problems, minimizes the errors, and is adaptive for future changes. And this way we can see these changes that I have shown, savings that I have shown you. This is the dashboard. It's fully integrated. The operate dashboard is fully integrated in the design dashboard and propose. So it's one product, and you can automatically move from the design platform into operate here. There's also some that we have logs there for microgrid operation, also for tracing back why there are differences. And of course, the forecasting is everything embedded in this system here. So to conclude this presentation, I want to point out again that a PV and battery system is really hard to manage because it's the most volatile system you can imagine. As soon as you get a generator into the mix, it's very stable and it stabilizes the system. And this is also why some generator manufacturer pushing their technology or want to have the technology in a microgrid, because it's stabilizing the system and it can also help the batteries in terms of lifetime. But from a control perspective, just being able to control a PV and battery with 80% saving is actually a challenge, which we have proven for our CalTestBed evaluation. The other thing is not all months are the same, because depending on the spread, as I already said, between on-peak and off-peak and the volatility, you will see less benefits in some months. This is why it's so important to actually design your system with Xendee design. And then before you go into deployment, to use real-time information, collected real-time information in an operate simulation environment to actually assess the benefits of your controller before you deploy the system. And this brings me actually to the end of my talk. I'm really happy and thankful for being here. And if you have some questions, just let me know. I'm happy to answer them. Thank you.